For decades, we have relied on classical computers to process information and solve complex problems. These machines, while impressive, are limited by their reliance on bits which can only represent a 0 or a 1. But what if we could harness the strangeness of quantum mechanics to create a fundamentally different kind of computer? This is the promise of quantum computing, a revolutionary technology poised to transform industries ranging from medicine to artificial intelligence. Quantum computers are not simply faster versions of their classical counterparts, they operate on entirely different principles. By tapping into the enigmatic world of quantum mechanics, these machines can perform calculations that are impossible for even the most powerful supercomputers. Imagine being able to design life-saving drugs, break the most sophisticated encryption codes, or model complex systems with unprecedented accuracy. This is the potential power of quantum computing. However, before we delve into the potential applications of this technology, it is crucial to understand the fundamental concepts that underpin it. Prepare yourself, for we are about to embark on a journey into the fascinating and often counterintuitive realm of quantum mechanics. At the heart of quantum computing lies the qubit, the quantum equivalent of a classical bit. While a bit can only exist as a 0 or a 1, a qubit can exist in a superposition, simultaneously representing both 0 and 1. This mind-bending concept is one of the defining features of quantum mechanics and is key to the power of quantum computers. Think of a qubit like a spinning coin. Until it falls flat, the coin is in a state of superposition, representing both heads and tails simultaneously. Similarly, a qubit can exist in a blend of states, allowing it to perform calculations on multiple possibilities at once. This ability to explore a vast range of potential solutions in parallel is what gives quantum computers their computational advantage. But the strangeness doesn't end there. Qubits can also be linked together through a phenomenon known as entanglement, creating a powerful interconnected system. Let's explore this fascinating concept further. To grasp the potential of quantum computing, we must embrace the concept of superposition. In the quantum world, particles exist in a haze of probability, occupying multiple states until measured. This fundamental uncertainty is not a limitation, but a source of immense computational power. Imagine searching for a specific grain of sand on a vast beach. A classical computer would have to examine each grain individually, a daunting task. However, a quantum computer, leveraging superposition, could analyze every grain simultaneously, dramatically reducing the search time. This ability to explore numerous possibilities at once allows quantum computers to tackle problems that are intractable for classical computers, such as factoring large numbers or simulating complex molecules. The implications for cryptography, drug discovery, and materials science are profound. Section 4, Entanglement, a spooky connection. If superposition is strange, entanglement is downright spooky. When two qubits become entangled, their fates become intertwined, regardless of the distance separating them. Measuring the state of one entangled qubit instantly determines the state of the other, even if they are light years apart. Imagine two coins flipped simultaneously, always landing on opposite sides. This is akin to entanglement. Measuring one coin instantly reveals the state of the other, regardless of their separation. This seemingly impossible connection is a fundamental feature of the quantum world. Entanglement allows quantum computers to perform operations on multiple qubits simultaneously, further enhancing their computational power. This interconnectedness is crucial for developing complex quantum algorithms and unlocking the full potential of this technology. Section 5, Quantum Computing Challenges and Opportunities. While the promise of quantum computing is immense, so too are the challenges. Qubits are incredibly fragile, susceptible to errors caused by environmental noise. Maintaining their delicate quantum states is a significant technological hurdle. Scalability is another challenge. Building large-scale quantum computers with thousands or even millions of qubits is a monumental engineering feat. Overcoming these challenges will require continued investment in research and development. Despite these hurdles, the future of quantum computing is bright. As we delve deeper into the quantum realm, we can expect groundbreaking discoveries and applications that will reshape our world. The journey has just begun, and the possibilities are as limitless as the universe itself.